good. Okay, sky this month, February the 12th to March the 12th, 2021. Not a whole lot going on actually in the sky. I've got Jupiter and Saturn are going to reappear. It seems like just a couple of months ago, we were all agog about Jupiter and Saturn having a conjunction, and then they disappeared into the sun, and now they're back, and they're reappearing and joining Mercury. So we'll talk a little bit about that. And then back in December, I talked about the lunar analemma, the fact that what the sun does in a year, the moon does in a month. And so there is kind of an analogous thing to an analemma in the moon, but we didn't really talk too much about the solar analemma, and so I'd like to go into that and maybe explain some things about that. So let's go. So first of all, this is the sky on February the 25th. So a couple of weeks from now at 6:30 a.m. Of course, as you know, as the weather gets better, the sun also rises earlier. So it means you've got to dig yourself out of the bed if you're going to see any of these sights before the sun gets up. But if you take a look in the southeastern horizon, you'll see Mercury and Jupiter and Saturn have now sort of made their appearance in the east, actually just a little bit east of southeast. So that's they're going to be there. They're going to be very low in the sky. So that kind of gives you an idea of where they'll be, and that's at your 10 degrees. So yeah, you're going to have a very good southeastern exposure. So I would recommend there's a beach at the bottom of I think it's Mason Road, and that's where Dan Kozlowski and I sort of watched the moon occulting Mars, I believe. And or you could go to that sort of breakwater at Roberts Creek, or you can, as long as the trees don't get in the way, I'm going to try and see if I can see them from my own porch.
Hey, there is another location. There's a nice flat paved area past the Langdale Ferry Terminal that has an easterly view that probably goes from directly east to slightly fairly northeast, and probably northeast to southeast, but it's elevated and it's exposed to wind a bit, but it's a nice clean flat area where you can set up a telescope, and it's got probably the best easterly view on the coast.
Is this so you go past the Langdale Ferry out towards the Port Mellon Mill?
That's correct. About somewhere between say 2 and 3 kilometers.
Okay.
It's called Cascadia Heights. It's like a partially sold real estate development. So they've got the road network in there, but they only have about 3 or 4 houses. They don't seem to have like ridiculously bright lights there. So
is it on the coast or the high side of the road? Seaside or the high side?
Oh, sorry, it's above the highway.
Okay.
Well, the Port Mellon Highway.
Right. Okay, thank you very much. Okay, so that's February the 25th, 6:30 a.m. Now, if we go to March the 5th, then it's kind of a nice view here, because by now Mercury will have moved basically as close as it's going to get to Jupiter a little bit earlier, 6:15 a.m. So it was kind of fun to spot Mercury because it's so elusive, and of course around here with clouds on the horizon in a lot of directions, a lot of times it's particularly fun. So Jupiter will guide you right to the spot of where Mercury is, and of course Saturn is up there. It'll be easier to spot even earlier than 6:15. So again, that's March the 5th, and then March the 9th. Mercury, of course, is again moving rapidly. And so it's now you've got a line of planets, and then the moon shows up, and it's just a very thin crescent moon. It's a dying moon, the old moon. And so it won't be, it won't be the problem. The problem will be the sun. So it's just kind of a nice little arrangement of these 3 planets and the moon. So that's March 9th. Mars is up in the sky, but that's not that's easy enough to find. So I didn't do any pictures of Mars. That's at night. Okay, so that's it for basically what's going to happen over the next month. Now I'd like to talk about an odd experience that I had when I was a school teacher, and that is that walking home on a trail after school in the winter, say I'd come home from school at about 5 p.m. And what I always noticed was that it was extremely dark in late November until the Christmas break. So, I'd basically be I'm walking along a trail through the bush, and it's basically, I'm just feeling my way. So it's virtually pitch dark. And then in the new year, things seemed lighter already, and yet it was only just a couple of weeks past the solstice, and it was a bit strange that it seemed to get light so quickly. Well, it turns out that the Analemma will explain what was going on. So let's turn to the Analemma. Now, this is a picture I think I showed to you when I was talking about the moon. And this picture was a shot of the sky taken every 2 days at exactly the same time of morning. And basically, what you would normally expect is that the sun would be low in the winter and high in the summer. But it's not obvious why you would get this figure 8 pattern. December the 21st, of course, is down at the bottom, and June the 21st is at the top. These are nominal dates. And winter is on that limb, and fall is the higher limb. So what that's basically saying is that oh, and by the way, that cross piece there, that's basically the equinox. So what it's telling you is that in January, the sun is behind where it should be. It's getting up late, and of course, therefore, it's going to bed late. And so that's why in January, I'm experiencing exceptionally light conditions given the time of year. Whereas if you look just on the other side in the fall, just a few weeks before December the 21st, the sun is early, quite a bit early, and therefore it's rising early and setting early, and that's why it's so dark when I'm coming home. And it's not just higher or lower in the sky, but it's earlier later in this somewhat complicated fashion. Sun late on the winter side and sun early on the fall side. So the same thing happens in the spring. The sun is a bit early, and in the summer, the sun is a bit late. So you can actually see the same pattern etched on globes, especially older globes. Basically, this analemma shows how much the sun differs from the clock. And this was in use all the time throughout the ages when they used sundials. They were aware that the sun is early or late, depending on what time of year. How they figured that out, I haven't determined yet, but they knew that. And so you'd consult what the time was on the sundial, and then you'd adjust it with the analemma. So the sun is behind the clock in January and February. Now, up where I've just pointed the arrow, there's a scale there, and it goes up as far as 20 minutes. But I think that the actual maximum is about 16 minutes behind schedule. So here we are down in the January, say January the 15th, and it looks like we'd be roughly 10 minutes early. So that would mean the sun would rise 10 minutes late, sun would rise 10 minutes late, and it would set 10 minutes late on January the 15th. Okay, so
Oh, that means my sextant is about 30 seconds slow. I'm just going to calibrate it now.
okay, okay. So that's why the walk home is lighter in January than it is in November. And but of course, that's a great explanation. But the question is, what's the explanation of the analemma? And it's something that there was a discussion on this on a radio about over almost 30 years ago. And there was all kinds of people coming up with contradictory reasons why this is so. So let's just kind of review some facts about the sun. So the ecliptic is the apparent track of the sun through the stars. We're going to take a geocentric point of view for this exercise. And so you have this ecliptic, and this is not the path of the sun during the day. The path of this sun during the day would be just basically straight across this map. But what would happen is, okay, so here we are, this is the ecliptic, there's the celestial equator. Here it is, February the 12th, that's where the sun is. And it's going to be moving east along the ecliptic. And eventually it's going to get to the equinox around March the 21st. And then it's going to keep going, steadily marching along the ecliptic until it gets to June the 21st, which is when it reaches its highest point above the equator. And although there's a certain amount of distortion that you can see in this picture, you can see that it has reached its highest point, given that distortion. It's reached its highest point on June the 21st, and then it's going to start to keep on following down, and it'll track down and back to the equator again. So that's the ecliptic. Now, I want to propose to explain the analemma to simplify the motion of the sun. We're going to assume that the year is exactly 360 days long, and you'll see why in just a second. So, and that the sun moves steadily around the ecliptic. Okay, so it doesn't speed up or slow down as it goes along the ecliptic. That means it goes exactly 1 degree per day in the eastern direction. 360 days, it's gone all the way around the ecliptic. That's 1 year. We're going to assume, however, that it's not completely a geocentric position, or it's geocentric but not geostationary. We're going to let the Earth rotate daily. And so as the Earth rotates daily, it has to rotate more than 360 degrees from noon to noon, because it's got to keep up with the motion of the sun. So it rotates 360 degrees and then another 1 degree to catch up to where the sun has moved a little bit farther east along the ecliptic. Okay, so that's our simplified motion. Okay, and just in case it's uncertain what I'm talking about here, we've got here's the sun, and the Earth is pointing at the sun, and the sun is going to move that far in a day. Well, that's rather an exaggerated amount that the sun moves. It would be just a tiny amount, but that's easy to illustrate. Okay, so what happens? Okay, the Earth goes around 360 degrees, but it's no longer pointing at the sun because the sun's moved another quarter of a turn. So it's got to move more than 360 degrees to go from noon to noon. That's what I'm saying by the Earth is going to rotate 361 degrees to keep up with the sun. Okay, so now let's look at the ecliptic at the March equinox. So that's this region here, and you'll notice that the ecliptic is sloping up. So we've zoomed in, and we need to take some measurements here. So that arrow represents 1 degree of latitude. It also represents 1 degree along a diagonal and 1 degree straight east and west. So each of those arrows is the same length. And so now this so happens is 5 minutes between those vertical lines. And 5 minutes means it takes the Earth 5 minutes to rotate that far. Okay, and 5 minutes is 1 1/4 degrees. normally the Earth normally the Earth rotates 4 minutes or 1 degree in a day extra. Okay. Okay, so here's the sun, and it's on the ecliptic, and it happens to be March the 19th. And it's going to move exactly 1 degree March the 20th. And then March the 21st, that's the equinox, it crosses the equator. And then it just keeps on going 1 degree each day. Now, it turns out in our simple theory or simple motion here that on the 21st of March at the spring equinox, it's lockstep with a clock. It will cross, if you choose your appropriate point on Earth, it will be directly overhead exactly when the clock reads 12 noon. Okay, so now what's going to happen? Well, the Earth is going to swing 1 degree directly east. But notice, because the sun was climbing up on an angle 1 degree, it hasn't gone 1 degree east. Some of that degree has been used to go north. And so on. That's the 22nd, the 23rd, the 24th, the 25th. The sun is falling farther and farther behind where it should be if it was a simple simple, but it's not. It's because it's on this angle. It's lagging behind the where it should be. Now, what does that actually mean in practice? Well, okay, the Earth is going to also swing to the east. So let's take a look at the 21st. It's going to swing all the way around back to the 21st, where the 21st is, and then it's going to go 1 more degree. And then that's noon, 12 o'clock the next day, 12 o'clock noon. But notice, in moving, it actually bumps into the sun before it bumps into noon. So that means that the sun is actually ahead of the clock at this point. The sun got up early. It crossed the meridian early. Okay, so when the sun is not keeping up, it actually is making the solar day shorter, and so it's crossing the meridian in less than 24 hours. I hope that's comprehensible. Does that make any sense, Don? Uncommitted? Okay.
I'm keeping up.
What's that?
I said I'm keeping up. That's good.
Yeah, okay, so it's important to get this, okay? Okay, so the next thing then is, let's summarize this. The ecliptic is tilted at the equinox. The sun moves 1 degree, but in an angle. Noon moves 1 degree due, I said west. That's wrong, it's east. The sun doesn't keep up. Therefore, the Earth rotates less than 361 degrees to point to the sun. Therefore, the solar day is less than 24 hours. And by the time you get to May the 8th, the sun is 10 minutes fast in our simple motion. It would be 10 minutes fast by the time you got to May 8th. So it would cross the meridian at 10 to 12. Okay. Now let's zero in on the ecliptic on June the 21st. Okay, so notice that the lines of longitude are squeezed as you go farther north. So there's the distance between the lines of longitude at the equator. But if we take that same arrow and put it north, it stretches farther than between those lines. And that's sort of obvious, right? As you go farther north, those meridians get closer and closer till finally they meet at the poles. So there's shorter gaps between the lines of longitude. But also, the sun is now moving due east. It's not tilted. It's going straight in the direction it's supposed to be going. And so that helps the sun make tracks. Okay. So here I've got 1 degree of latitude. 1 degree of latitude is the same no matter where you are. this is 1 degree along the ecliptic. And of course, 1 degree on the ecliptic is the same as 1 degree of latitude. 1 degree is 1 degree. But then this is 1 degree of Earth rotation because of the narrowing of those longitudinal lines. So what does that all mean? How does that translate? Okay, well, here we are. It's June the 19th. And we go 1 degree along the ecliptic, June the 20th. And then June the 21st, 22nd, 23rd, 24th, 25th. Now, it turns out, and in our simple motion, on the 21st, the sun will be once again in lockstep with the clock. 12 noon, it crosses the meridian. And then the Earth rotates 1 degree of Earth rotation. That's not that far because the lines of longitude are close together. So that's the 22nd, the 23rd, the 24th, the 25th. So what's happening now, as the Earth goes around 361 degrees, it still hasn't caught up to the sun. The sun's going to be late. It's not going to cross the meridian until after 12 noon. Okay, what's happening now? What's going on here? Whoops. Okay, so let's summarize. First of all, in June, the ecliptic is not tilted. The sun moves 1 degree due east. Meridians of longitude are more closely spaced than at the equator. So the sun races ahead of the Earth's rotation, and Earth must rotate more than 361 degrees to face the sun, and therefore the solar day is greater than 24 hours. And by August the 8th, the sun is 10 minutes behind the clock. So that means that at 12:10, the sun will cross the meridian instead of at 12 o'clock. Okay, so I've drawn here a sort of a scale diagram of what that would actually mean. There's your 23.5 degrees above the equator for June, and your 23.5 below for December. And then the width there represents 10 minutes of gain, or 10 minutes ahead or 10 minutes behind where it should be, 10 minutes late, 10 minutes early, 10 minutes late and 10 minutes early. Yeah, okay. And as we fill that in, let's see. This is an analemma for a circular orbit. I don't know where to put this. Oh, there, that's better. Okay, analemma. Okay, and then this is looking east at sunrise, the same as that picture I showed you. Sun's going in this direction. So in the spring, it's ahead of time. In the summer, it's behind time. And in fall and winter, you get the same pattern. In fall, the sun rises ahead of time and of course sets ahead of time. And in winter, it rises behind schedule and sets behind schedule. Okay, so when you take a look at a real analemma, it's not nice and symmetrical, it's lopsided. So what's the problem here? Well, it's that the Earth's orbit is not circular, but elliptical. So it's actually closest to the sun on this year, on January the 2nd at 11:57 a.m. So that's when it's closest to the sun. And Earth moves faster when it's closer to the sun. So that means that the sun moves faster along the ecliptic. Now, what does that mean? Well, it means, for one thing, that the spring and summer is longer than the fall and the winter. And that's kind of nice. There are, just added up, there are 4 spring summer months that have more than 30 days. So March, May, July, August. 4 months have 31 days, plus all the ones that have 30, that adds up to 184 days total. But if you look at the winter months, there's October, December, and January. have 31 days, but then you got to subtract the 2 off of February. So that only gives you 1 day extra total. So that's 181 days. You add those 2 up, you get you 365 days. So basically, we have long spring summers and short fall winters. Of course, in Australia, it's the opposite. Okay. Well, the slow motion along the spring summer ecliptic shortens the solar day. When the sun is not going as fast, it makes the day shorter. Rapid motion along the fall winter ecliptic lengthens the solar day. Now, this is actually a plot that shows the 2 effects. You can see this effect here up and down like that. That's assuming that there was a perfectly circular orbit of the sun. And this long thing here, that is the ellipse, the elliptical orbit, here's the sun speeding up and therefore making the day longer. And then here it's slowing down and making the day shorter. And then this is the combined effect. Okay, and you'll notice that the combined effect means that you get somewhat around 16 minutes in November, 16 minutes ahead of time in November, and you get about 14 minutes behind time late in late February. That's where we are here. So it tends to exaggerate the winter swings, and it kind of suppresses the summer swings. Okay, so hang on. So it exaggerates the short fall days and the long winter days, and it suppresses the short spring days and the long summer days. So that's how you get that lopsided picture. So that's what I have to say. I hope that thoroughly explains for you the analemma. I hope you have a great time observing this month. It's a better time than you had in January. And I hope to see you on March the 12th. And I thought, sorry, here's our Zoom link. But I thought Charles was going to give a presentation.
No, I don't have one for you tonight, Bruce. I'm going to be doing next month.
Oh, okay. And Bill, of course, you won't want to miss what Bill's got to say about his new toys. Okay, thank you very much.